In this video, we're going to look at the reactions of esters. So we're going to study the carboxylic acid derivative of esters. And we've already seen that esters are less reactive than both acid chlorides and anhydrides. And so because of this, they cannot be used. We saw that, anhydrides, you can't make acid chlorides because of the reactivity difference. So esters cannot be used to make acid chlorides, and they cannot be used to make anhydrides. However, they still can be used to make amides, and they still can be converted to carboxylic acids. So you're kind of seeing, I hope, that as you move to a carboxylic acid derivative that is more and more stable, the reactivity becomes less and less, and so the number of reactions actually decreases. So let's look at hydrolysis of esters first. We see that we're going to see that esters can form carboxylic acids in either acidic conditions or basic conditions, and the mechanism is going to be similar, but there's going to be some slight variations, and you need to recognize what those variations are. And so you can certainly, I could ask you what the mechanism of acid hydrolysis or base hydrolysis is, and you should be able to tell the difference between the two. So let's look at acidic hydrolysis first. The first thing is that you take the ester, and of course if we're in acidic conditions, we're talking about hydrolysis, which means that you're hydrolyzing the ester to a carboxylic acid. So this is done in water, hydrolysis in water, using an acid. And of course we then, as our acidic source, we could use the hydronium ion. That's going to be present. So the acid may be sulfuric acid as a catalyst. It could be a number of acids as catalysts, and of course we know that the acid catalyst is going to, or the acid is going to react with water to produce the hydronium ion. So it's very easy to simply use the hydronium ion as your acid source. We should know by now that when you have a carbonyl compound in the presence of an acid, the oxygen gets protonated, and that's certainly what happens, right? So you have a proton transfer to the oxygen, and it produces our now protonated version of the ester. And of course that increases the electrophilicity of the carbonyl carbon. So now water, which isn't a great nucleophile, is certainly good enough to now attack the carbonyl carbon, displacing that carbon-oxygen bond. And so you generate a tetrahedral intermediate that has a positive charge to it. So this would be referred to as a Ti plus, and we can deprotonate the one of the hydrogens with water, right? Because we have a lot of water. We're doing hydrolysis in water. So water can deprotonate that hydrogen, and we generate our Ti. So this is a Ti, and the Ti is a neutral species. And now that Ti can get protonated, because notice we regenerate our acid in the process. Water deprotonates that Ti plus, and now we generate the hydronium ion, and we're regenerating our acid. And of course, any one of the three oxygens can get protonated. So this is an equilibrium process, as we know. We've already seen that carboxylic acids will react with alcohols to produce esters, and now this is essentially the reverse mechanism. Esters are reacting with water in the presence of an acid to generate carboxylic acids. So we know that either one of those three oxygens can be protonated, and if an OH gets protonated, then it's going to shift the equilibrium back. But if the OR gets protonated, then we generate this species, right? So Ti, another different Ti plus, where we have a good leaving group of an alcohol. So the alcohol is a good leaving group, and it certainly leaves. So we're going to then donate a pair of electrons from one of the OH groups and kick off our alcohol, and we generate now our carboxylic acid that is protonated plus alcohol. And so now we simply have to deprotonate that oxygen there, and we could use the alcohol that we just generated. We could use water, it doesn't really matter. So I'm just going to use the alcohol that came off, and I generate my carboxylic acid plus alcohol. Now the alcohol is protonated, and of course that proton could be anywhere. Usually it's chances are likely that it's generating the hydronium ion again. But I'm just showing you that you have an alkyloxonium ion present as well. All right, so we see that esters react with water to produce carboxylic acids. We've already seen in a previous chapter that carboxylic acids react with alcohols to produce esters, and of course we can control our product based on the solvent that's used and driving the equilibrium to where we basically want it to. And that's kind of the nice thing about equilibrium reactions. All right, so I said we can hydrolyze in acidic conditions. We can also hydrolyze in basic conditions. When we talk about basic hydrolysis, we actually have a name for this, and it's called saponification. And saponification, that term actually comes from the fact that soaps are made from fatty acid esters. So fats are esters. And when you take a fat and you add base to it, you get a soap. And so that process is called saponification. And in general, when you take any ester and you react it with a base, it's called saponification. And in that step, or in that process, hydroxide, the base, isn't catalytic. And so a carboxylate forms. Now because of this, the reaction itself is not reversible, right? So this is very important to understand. Saponification actually is the best way of hydrolyzing an ester because you don't have that equilibrium process taking place. Now, also because of this, though, I said it generates a carboxylate. So if you want a carboxylic acid, then you have to have an acidic workup to get that acid, to generate that acid. And the mechanism of this is actually fairly simple. You should be able to think about this mechanism without me even going through it by now. But of course I'm going to go through it with you just so you can see, for those of you kind of struggling with these concepts still. In basic conditions, we have water and we have hydroxide, right? So the hydroxide ion is a better nucleophile. We're not protonating the carbonyl oxygen because we're not in acidic conditions. Hydroxide is a good enough nucleophile to simply attack the carbonyl carbon, displacing the carbon-oxygen bond. And so we're generating a Ti minus. Notice in acidic conditions we're always generating Ti or Ti pluses. In basic conditions we generate Ti minuses or Ti's. So in basic conditions, with the Ti minus, we have an OR that could come off, and it certainly does. It's not an extremely fast process because alkoxides aren't the greatest leaving groups, but with a little bit of heat, typically saponification involves a little bit of heat, then you can lose that alkoxide and regenerate the carbonyl. So the product of that is a carboxylic acid, but of course we're in basic conditions. So either hydroxide can come along and deprotonate that, or the alkoxide that we just generated that came off is also a very good base, and so it can also remove a proton from the carboxylic acid, and we generate a carboxylate plus the alcohol that is from the alkoxide that got protonated. So now that carboxylate simply sits there, and you see that one equivalent of hydroxide has been consumed, and it's not catalytic. In order to generate our acid, we have to add an acid to that. So we basically have to neutralize all of the hydroxide with a strong acid until all of the hydroxide is neutralized. Then we start to protonate the carboxylate, and we can generate a carboxylic acid this way. So again, this is actually probably the best way of hydrolyzing an ester because it's an irreversible reaction. But it does involve a neutralization and acidification of the reaction mixture. And so it's usually shown in two steps. One, sodium hydroxide water. Two, H3O plus, right? Adding some type of acid, H2SO4 usually is the acid of choice in these acidic workups. Now, another reaction of esters is what is called transesterification. And in a manner very similar to hydrolysis in acidic conditions, you can take an ester and you can treat it with an excess of alcohol. So instead of water, we're using alcohol catalyzed by an acid or base. Typically, acids are used in these processes. And what happens is you're transesterifying, so you're switching the ester groups essentially. You take an ester, you react it with an excess amount of alcohol in the presence of a catalyst, and you generate a new ester, right? With the alcohol of the original ester coming off. And so in either acidic or basic conditions, these are catalytic conditions. So either way, the reaction, we still have that kind of reversibility taking place, but again, adding an excess amount of alcohol is going to shift the equilibrium to the product formation. So here's an interesting example. I have an ester that is a cyclic ester, so it's called a lactone. So if I take a lactone and I treat a lactone with methanol, an excess amount of methanol with an acid catalyst, what happens is I'm going to make a methyl ester, and the oxygen, it actually is still connected to my structure. So I generate an alcohol at the end of that chain, and notice I make a methyl ester this way. All right, now I said at the beginning, esters make carboxylic acids, they make amides. And so we see that esters will react with amines to yield amides, right? Very similar process as that of acid chlorides and acid anhydrides. Esters will react with an amine and you generate an amide plus the alcohol. So OR is coming off and then it can get protonated. These are generally done with some acid catalyst. Sometimes a basic catalyst, it's going to kind of vary and it's not really crucial to understand. What's crucial to understand is that you have an amine, it's reacting with an ester, it's going to produce an amide. So here I have an example of a propyl butanoate reacting with ammonia at minus 78 degrees, and I'm going to generate butanamide. Butanamide plus propanol comes off. So those are the main reactions of the carboxylic acid derivatives. Esters react with water in basic or acidic conditions to produce carboxylic acids, and they react with amines to produce amides. And of course, we can also think about them reacting with organometallics, just like we talked about acid chlorides reacting with organometallics. Esters will also react with organometallics. And so we can take a look at those types of reactions. And the first one we'll take a look at is esters reacting with organolithium and Grignard reagents. And just like with acid chlorides, they give tertiary alcohols. The mechanism is identical to that of the reaction of acid chlorides. So remember I said, there's a lot of reactions, but the mechanism of the reactions is all very similar. And so if you get the hang of the mechanism, then you can be able to predict anything that you want. That's the key to chapter 18. That's definitely the key. So here I have a generic ester reacts with two equivalents of our Grignard reagent or organolithium reagent, followed by an aqueous acidic workup, and it generates a tertiary alcohol, right? So that's the key. It's tertiary alcohol, and two R groups are adding to that tetrahedral carbon. And I'll go through the mechanism of this just to, show you kind of the pattern, re-show you the pattern so it sticks more and more in your head. We have an ester, just like we had an acid chloride. We have an ester. It reacts with a nucleophile. The nucleophile is, in this case, a Grignard reagent. That Grignard reagent attacks the carbonyl carbon, displacing that carbon-oxygen bond and generating a tetrahedral intermediate, Ti minus. So now the Ti minus is formed. We're going to kick off OR minus, regenerating the carbonyl, and we generate that's right, ketone. And what do we know about ketones and Grignard reagents or organolithium reagents? Well, ketones will react with Grignard reagents. And so we get another addition to generate another tetrahedral intermediate. But now this time we don't have a good leaving group. The alkyl groups, we have 3 alkyl groups. None of them are good leaving groups. And so instead of the carbonyl reforming, we simply protonate. It just stays that way as an alkoxide until we add some acidic aqueous workup. And then we get proton transfer occurring, and we generate our tertiary alcohol, right? So let's look at an example. Here I have a methyl ester, and I'm reacting it with 2 equivalents of ethyl magnesium bromide in THF, followed by an aqueous acidic workup. So I'm going to be adding 2 ethyl groups to the ester acyl group, to the carbonyl group, and I'm losing the methyl or the methanol in its place. Right, so the acyl group becomes an alcohol. I've added 2 ethyl groups to my product. That is my tertiary alcohol. And just like acid chlorides will react with lithium aluminum hydride, so will esters react with lithium aluminum hydride. And again, they produce primary alcohols. Notice that sodium borohydride cannot be used in this process. So we see sodium borohydride can't be used to reduce carboxylic acids. They also cannot be used to reduce esters. And they really can't be used to reduce acid chlorides as well. So there's some selectivity there, right? Sodium borohydride isn't a very strong reducing agent. It will reduce ketones. It will reduce aldehydes, but it won't reduce carboxylic acids or carboxylic acid derivatives very well. So, whenever you think about grouping things together, you should think about some type of selectivity as well. And in general, we have an ester reacting with lithium aluminum hydride in some aprotic solvent, followed by an aqueous workup, and we generate a primary alcohol. And again, the mechanism of this is going to be very similar to the mechanism of acid chlorides reacting with lithium aluminum hydride. So let's again just kind of take a look at that mechanism where you have now this time an ester reacting with the aluminum hydride. It's going to donate a hydride, to the carbonyl, and we generate our tetrahedral intermediate, where now we have hydride being added. That's the nucleophile. And so the alkoxide OR is a good enough leaving group. We regenerate our carbonyl and we displace OR minus, and we have formed an aldehyde. And just like with acid chlorides forming aldehydes, esters also form aldehydes as well, and so that aldehyde can react with another equivalent of aluminum hydride, and we generate the alkoxide, where now we have two hydrogens being added to that tetrahedral carbon. Neither one of those hydrogens is a good leaving group, and the R group is not a good leaving group, and so it simply sits there as an alkoxide until we protonate it, right? We add an acid, and then we get protonation to generate a primary alcohol, right? So let's look at an example of this. Here we have an ethyl ester reacting with lithium aluminum hydride and THF, followed by an aqueous workup. And so we're going to reduce the carbonyl. We get an alcohol, and of course the ethyl alcohol also comes off. So we end up with two alcohols in this process. One where the ester portion, the ethyl ester portion, actually is coming off and gets protonated in water, and then one where the carbonyl is actually reduced. So keep this in mind. You know, you're generating two alcohols. I guess that might be the trickiest part of it. Now, we talked about acid chlorides being reduced to aldehydes using some reagents of some hydride reagents that only have one hydride, right? The lithium aluminum tert butoxyhydride as our reagent. And for esters, esters also have specific reagents that can do the same thing. So we can use reagents like diisobutyl aluminum hydride. Diisobutyl aluminum hydride is often abbreviated dibol H. So typically we say dibol. Whenever you hear the term dibol, it's a reducing agent. And we can use this to reduce esters to aldehydes, and the reaction stops there. And so the typical reaction scheme looks like this. You're taking an ester, you're reacting it with dibol H, followed by an aqueous workup. Now, dibol, for those of you that are fascinated with looking at structures, is this. It's not an so it has a hydride source to it, but the aluminum actually is neutral in this type of species. So it is a hydride, but it's not like the aluminum hydrides that we've seen before. And number one, it's slightly less reactive, and so it doesn't react with ketones. It doesn't react with aldehydes to reduce them, but it is reactive enough to reduce an ester. So the hydride adds to the carbonyl, the OR comes off, you generate an aldehyde, and then that aldehyde basically is unreactive toward dibol. And so you end up generating just the aldehyde. So the aldehyde doesn't get reduced. An example of this would be this particular ethyl ester reacting with dibol H, followed by an aqueous workup, and we get our aldehyde as our product. And that wraps up the reaction of esters.